This webcast talks about how to make a force diagram. A force diagram is sometimes called a free body diagram. So a force diagram is a diagram of all of the external forces that are acting on an object. So in this little example, I've got a monkey hanging from a vine. So the external forces would be forces that are being applied by objects that are outside of the monkey on the monkey. So for example, the monkey has a weight. So there's a force of gravity equal to the monkey's mass times the acceleration due to gravity, and that points down to the center of the earth. And then the monkey is holding on to a vine, and so there are tension forces in the vine, and they both are directed in the direction of those pieces of vine, and they're holding the monkey up. So there may be other forces, such, internal to the monkey. For example, the monkey's little heart or the muscles or things like that. But when we do a free body diagram, we are only showing forces that are being exerted by objects that are outside of the object that we're looking at. When we draw a force diagram, we want to be very careful to label the forces, showing the type of force and the names of both of the objects that are interacting. So the label will include the type of force, what object the force is acting on, in other words, the victim of the force, and then what object is exerting the force, in other words, the agent that is exerting the force. So for example, the weight of that monkey would be F sub g, because it's a gravitational force, comma monkey, because the monkey is who the force is being applied to, comma earth, because the earth is the object that is exerting that force. Here in this example, we have a little girl dragging a box across the floor. And so if we looked at this force diagram, there is the weight of the box. That's the gravitational force that the earth is exerting on the box. The little girl is pulling the box to the left, and so we have a frictional force that's being exerted on the box by the floor, and that frictional force opposes the sliding motion of the box, so it points to the right. The girl is using a rope to pull the box, and the rope is angled up a little bit, right? And so there's a tension force that the rope is exerting on the box, and it is in the same direction as the rope. And then the box is sitting on the floor, and so there is a normal force that the floor is exerting on the box. So when you create a force diagram, you always want to draw a set of coordinate axes with one axis parallel to the direction of motion. You'll draw a small box at the origin that represents the subject of the force diagram. Then you will represent all of the external forces on the subject using an arrow that starts inside that box and points in the direction that the force acts. And if you have forces that are equal and opposite to each other, you will use congruency indicators to show that those forces are balancing. Let's go to worksheet 4D, and let's draw some force diagrams to give some examples here. So in the first example, we have a cat who is sitting motionless on the rug. So since the cat is not moving, it says it's motionless, then I know, even before I analyze all of the forces, that the net force is 0, right? The balanced force model tells me that if I know that the velocity is constant, in this case the velocity is constant at 0, then I know that the sum of the forces must be 0. Okay, but I'm going to draw some coordinate axes here. I'm going to put a little box at the center. That represents the cat. Okay, so, and then I want to put all of the forces that I know about. Well, I know that the cat weighs something. So the weight of the cat is a gravitational force that's being exerted on the cat by the earth. And the cat is not falling through the floor because there's a normal force that's being exerted on the cat by the floor. And I think these may be the only two forces. And since the net force, the sum of the forces, has to equal 0, then I know I'm going to put congruency marks because the normal force is being balanced by the gravitational force. Okay, so those two forces add up to equal 0. Let's look at another example. Here we have a skater moving at a constant speed across frictionless ice. Okay, so I'm going to do a set of coordinate axes, and I know that the skater has a weight, so there's a force of gravity being exerted on the skater by the earth, and I know that the skater's not falling through the ice because there's a normal force being exerted on the skater by the ice. And it tells me that there is no friction, and so I won't have any friction that's opposing her motion. And I think that these two forces are balancing each other. The reason is there is no motion in that vertical direction, right? And so I'm going to write up here in the right-hand corner, the net force equals 0. Her velocity is not changing because all of the forces acting on her are balanced. They add up to 0. What about this one? Here we have a softball player who is slowing down. Her speed is changing. She's moving more slowly as she slides into base. So let's look at the forces in this situation. So the softball player has a weight. That's the force of gravity on the player, and it's being exerted on her by the earth. She's not falling through the ground because there's a normal force being exerted on the player by the ground. She's moving to the right, right? But her feet are sliding on the ground, and so there is friction. So there is a friction force on the player that's being exerted by the ground. And that friction force opposes the direction, opposes her motion to the right, so it goes to the left. Now, since there is no motion vertically, right, she's not levitating above the ground, she's not falling into the ground, the net force in the vertical direction is 0. So the normal force and the gravitational force are balancing each other, and so I'm going to put congruency marks there. There's one force left over. There's nothing balancing the friction force, and so the net force on this girl is to the right. I'm sorry, to the left. I don't know why I just said that. Is to the left, right? There's no balance to that frictional force. There's nothing that's making it add up to 0. So there is a net force in the horizontal direction. The net force in the horizontal direction equals the force of friction. Let's look at a couple of other examples. Here I have a chandelier that is suspended motionless from the ceiling. It's not moving. And it's being held up by this chain. So I know that the chandelier has a weight. That's the force of gravity. I'm going to call it light because that's easier to write than chandelier. So there's a force of gravity on the light that's being exerted by the earth. Now, there's something that's balancing that force of gravity, right? The chandelier is being held up by this chain, and a force that's transmitted by a chain or a rope or a cable is called a tension force. So there's a tension force being exerted on the light by the chain. And those two things are balancing each other. So the net force is 0, which it has to be if that light is not moving. What about here? We've got a bucket of water that's being raised at a constant speed. And it's moving up in the same direction, right? It's being pulled upward. Now in this case, let's be clear what we're doing a force diagram of. I'm just interested in the bucket. So I'm going to draw a circle around that. That's what I want to show the external forces on. So, well, that bucket of water, it has a weight. So it's the gravitational force that's being exerted on the bucket by the earth. And it's moving upward because there is a tension force being exerted on the bucket by the rope. There are no other forces, right? There's nothing pushing it to the left or the right, whatever. And since it's moving at a constant speed in one direction, its net force is 0, and that tension force and gravitational force must be balancing each other. What about this one? Here we have a skydiver. They've just jumped out of the plane and they are still speeding up. Okay, so that tells me net force is not 0, right? Because the velocity is not constant. But let's look at the forces on here. So, there's a weight, which is gravitational force on the skydiver by the earth. It tells me that air resistance should be considered. Now, in many situations, like when you are walking around or when you drop a ball or even throw a ball, air resistance, which causes drag force, is so small that it is usually ignored. But when things move quickly through air, there is a significant amount of drag. And so since it's telling me air resistance should be considered, I'm going to show a drag force. The drag force always opposes motion. So the gravitational force is making the skydiver fall down, so drag force is pointing up. And that's a force that's being applied on the skydiver by the air that's around him. Now, since they're speeding up, these two forces are not balancing each other. And in fact, we have to have a net force in the direction of acceleration. So the net force in this situation is pointing down. The gravitational force is bigger than the drag force, and that's why that the skydiver is still speeding up. Now here's a skydiver, but they've deployed their parachute, and so now it says, oh, now they're descending at a constant velocity. Okay? And so they still have the same force of gravity. But now the force of gravity is being balanced by the drag force. And so these two balance, and the net force at this point of time is 0. This really does happen in skydiving. You reach something called a terminal velocity. That's where drag is balancing the gravitational force, and from that point on you've gotten fast enough that your drag force is balancing the gravitational force, and then you fall at a constant velocity. Let's look at 8. Here we have a ball that's been thrown up like a baseball. And so if you look at it, notice the hand is not in the picture. We're looking at it after it has been thrown. So I know that it has a force of gravity, but there are no other forces on it. It says ignore air resistance, right? So there's no drag. There's no applied force. The person is no longer pushing it up. The only force we have on this ball is the force of gravity, and so the net force is pointing downward. This is a situation called free fall. That's a situation where the only force is Fg. That's called free fall. Okay, so here's the same ball, but now we're looking at it at the top of the parabolic, the peak. And we learned something about that, right? We know that the velocity at the peak is 0. So does that mean have the forces changed? Here's the force of gravity on the ball by the Earth. Has something changed from the one above? Nope, not at all. It's still in free fall. And so the net force is still pointing down. It's still in free fall. So the velocity is not really telling us anything about what the force has to be. Okay. And then let's look at 10. So we've got Jane pulling a wagon to the right, and it moves at a constant velocity. It tells us even that the velocity is 1 meter per second. And we're going to do a force diagram for the wagon. So I'm just doing for the wagon. So there's a force of gravity on the wagon. That's its weight. That's being applied by the Earth. And I'm just going to draw this to the left, but there's an applied force being applied on the wagon by Jane. There is a normal force, right? The wagon is not falling through the ground because the ground is supporting it with a normal force. And then the wheels are sliding along the ground, so there is a friction force being exerted on the wagon by the ground. Since it tells me that this wagon is moving at a constant velocity, I know that the net force must be 0. Therefore, in each direction, these forces are balancing. So in the vertical direction, the normal force is balancing the force of gravity. And in the horizontal direction, that applied force that Jane is pulling on the wagon with must be balanced by the force of friction. Notice I use double congruency marks there just to differentiate the horizontal forces from the vertical forces.